All right, buckle up, because today we're going deep, diving deep into the world of train tracks, and
Must be.
it's way more interesting than it sounds.
You've got that stack of engineering papers right there.
Yeah.
We're going to break down the forces at play, the clever design secrets.
And everything in between.
I love it.
By the end of this deep dive, you'll be able to drop some serious train track knowledge.
What I find fascinating is how often we take for granted the engineering beneath those steel rails.
You know, we see a train zoom by,
Yeah.
but we rarely consider the intricate dance of physics happening just below.
It's true. So let's start with the track system itself. We're not just talking about laying down some metal on the ground.
Right.
It's about the rails, the sleepers, the ballast, a whole system working together.
Exactly. Picture a cross-section of a track.
You've got the rail on top, of course.
But underneath, it's resting on these sleepers,
Okay.
almost like beams spaced out at regular intervals.
And those sleepers, they're nestled in a bed of ballast, which is usually crushed stone.
Yeah.
It's like a carefully crafted layer cake, and each layer has a very specific job to do.
Especially when it comes to distributing the immense weight of a train.
Okay, let me guess. It's all about spreading that weight out as much as possible.
You got it. Think of it this way. You wouldn't want all that weight concentrated on just the rails, right?
Right.
That would put enormous pressure on the ground
Yeah.
and could even cause the tracks to, like, sink.
So it's like wearing snowshoes in deep snow.
Yeah,
Spread the load, baby.
exactly. It's a brilliant feat of engineering, honestly.
A 10-ton load on the rail, for example.
Gets distributed through the sleepers and into that wide base of ballast,
By the time that force reaches the ground, it's spread over a much wider area.
drastically reducing the pressure.
That is seriously cool. It reminds me of those physics demonstrations where they have like a heavy object and it doesn't break a thin sheet of ice
Right.
because the weight is distributed evenly.
Speaking of weight, what about axle loads?
Yeah.
I've heard that term thrown around, but I'm not entirely sure what it means.
Axle load is simply the weight carried by each axle of a train.
Okay.
And it's a critical factor in track design.
The heavier the load, the more stress on the entire system.
That makes sense. More weight, more stress.
So I imagine there are limits to how much weight a track can handle.
Absolutely. And that's where it gets really interesting.
You see, the relationship between axle load and stress on the tracks isn't a one-to-one thing.
It's not like if you double the weight,
Yeah.
you simply double the stress.
Wait, really? What happens then?
It actually grows much faster than that. We're talking exponentially.
So doubling the axle load might actually quadruple the stress on the track, or even more.
Wow, that's kind of mind-blowing. It's like the heavier the train gets.
The more those stresses multiply like crazy.
Exactly. It's this delicate balancing act for engineers,
Trying to maximize efficiency by carrying heavier loads.
but also respecting the physical limitations of the track.
It's like a high-stakes game of Jenga, with the train riding on top. One wrong move, and the whole thing could collapse.
That's a great analogy. It highlights just how crucial meticulous engineering and careful load management are in railway design.
Okay, so we've got this whole system for managing weight.
But trains move, obviously. And those wheels aren't just simple cylinders rolling down the track, are they?
Not at all. This is where we get into some really cool physics.
Train wheels are subtly conical, meaning they're slightly wider at the base than at the top.
And that subtle cone shape.
Combined with the fixed distance between the rails, also known as the track gauge, is what allows the train to move smoothly.
Hold on, I'm picturing this cone shape.
And the fixed tracks, but I'm not quite seeing how that translates to smooth movement.
Well, it's all about the subtle interplay of forces.
As the train moves down the track,
Okay,
it naturally wants to go in a straight line, right?
that makes sense.
But here's the thing. That slight conical shape of the wheels, combined with that fixed track gauge, actually causes the train to move in a very slight zigzag pattern.
Wait, zigzag? You're saying trains don't actually move in a straight line?
It's more of a subtle sinusoidal wave than a true zigzag, but yes.
As the train leans slightly to one side, the wider part of the cone on that side makes contact with the rail.
This subtle change in contact point creates a self-correcting mechanism.
Gently steering the train back towards the center,
So this subtle conical shape
which you can't even really notice by just looking at it.
is crucial for keeping the train stable.
Precisely. It's a brilliant bit of engineering that uses the laws of physics to create a self-correcting system.
That's amazing. Now I'm really starting to appreciate the hidden complexity of something as seemingly simple as a train track.
Okay, so we've talked about the conical shape of the wheels and this track gauge.
But is there a standard size for the distance between those rails?
You're right to be curious. There is a standard gauge, 1.435 meters, and it's the most common gauge worldwide.
However, it's not as simple as one size fits all.
Uh-huh. I had a feeling there might be some exceptions to the rule.
There are always exceptions, and in the case of track gauges, those exceptions are rooted in a fascinating mix of history, geography, and even a bit of politics.
For instance, Russia uses a broader gauge, and there are narrow gauge systems commonly found in mountainous areas.
So different strokes for different folks or different tracks for different landscapes.
Exactly. Each gauge has its own advantages and disadvantages.
And the choice often boils down to factors like terrain, cost, and the historical context of the railway's development.
This is already blowing my mind. And we haven't even touched on passenger comfort yet. Is that where the smoothness of the ride comes into play?
Absolutely. Passenger comfort is a fascinating area because it's all about managing those unseen forces.
The vibrations and oscillations that we feel during a train journey.
So, what makes some train rides smoother than others? Spill the secrets.
It all comes down to understanding the concept of sprung and unsprung mass.
And how different frequencies of vibration affect us humans.
Okay, you've definitely piqued my interest. I can't wait to hear more about this.
But I guess we'll have to save that for part 2 of our deep dive.
So picture this. You're on a train and you feel a slight bump.
Okay.
That bump affects different parts of the train in different ways.
And it all comes down to whether we're talking about sprung mass or unsprung mass.
Okay, I'm picturing myself on a train feeling a bump.
But I'm drawing a blank on sprung versus unsprung.
Think of it this way.
Yeah.
The wheels, axles, and everything directly connected to them, that's your unsprung mass.
They're directly in contact with the rails.
Okay.
So they feel every single imperfection in the track.
Right, they're taking the brunt of the impact.
Exactly. Now, the sprung mass is the train car itself where the passengers sit.
It's separated from all that unsprung mass by a suspension system,
Okay.
usually made up of springs and dampers.
Ah, so the suspension is like a buffer between the passengers and those bumps.
You got it. It absorbs some of the shock from those bumps, making for a smoother ride.
But here's where it gets really fascinating. Different frequencies of vibration affect us humans in very different ways.
So it's like how some sounds are more jarring than others.
Precisely. Our bodies are more sensitive to certain frequencies.
And it turns out that vibrations around 5 hertz are particularly uncomfortable for us.
5 hertz? That doesn't seem very fast.
You might think so, but at that frequency, it feels more like a sharp jolt.
Higher frequencies, on the other hand, tend to be more tolerable.
So it's the difference between a deep rumble and a high-pitched whine. We can handle the whine, but that rumble gets to you.
Exactly. And that's why engineers put so much effort into minimizing those jarring 5 hertz vibrations.
So how do they actually do that?
It's all about designing the suspension systems to dampen those specific frequencies.
They take into account the weight of the train, the stiffness of the track.
A whole host of other factors.
It's a delicate balancing act, but
Yeah.
when it's done right...
You get a smooth and comfortable ride.
So a smooth train ride isn't just about having comfy seats. It's about invisible forces and frequencies we don't even realize are there.
Precisely. And it really highlights the incredible engineering that goes into something we often take for granted.
Speaking of things we've taken for granted, remember how we were talking about track gauge, the distance between the rails?
Yeah.
The standard gauge seems to be the most common, but you
Ugh.
mentioned some intriguing exceptions.
Yes, track gauges.
It's a fascinating story.
Full of historical quirks and geographical constraints.
All right, you got to tell me more. I'm hooked.
Well, let's start with the standard gauge, 1.435 meters.
It became dominant in the early days of railways, thanks in part to the influence of British engineers.
At the time, it offered a practical balance of stability and speed for the trains they were building.
And it just sort of caught on from there.
Pretty much. As railways expanded across the globe.
They often stuck with the standard gauge.
However, there were some notable exceptions.
Russia, for example, adopted a wider gauge, 1.520 meters.
Why go with a wider gauge? Was it purely for practical reasons?
There were some claimed benefits.
Like increased stability, especially at higher speeds?
But there's also a historical and geopolitical angle to consider.
Russia, with its vast distances and often harsh climate.
Wanted a railway system distinct from its European neighbors.
So the choice of gauge wasn't just about engineering, it was also influenced by geography and even a bit of strategic thinking.
Exactly. It's a perfect example of how seemingly technical decisions can be intertwined with broader historical and political contexts.
That's fascinating. So what about those narrow gauge systems I've heard about?
Narrow gauge railways, typically with gauges less than 1 meter, are often found in mountainous regions.
Why is that?
It all comes down to navigating challenging terrain.
The narrower gauge allows for tighter turns.
making it easier to lay tracks through mountainous areas with sharp curves and steep gradients.
So it's a trade-off. You might not be setting any speed records.
But you gain maneuverability in those tricky landscapes.
Exactly, and that highlights a crucial point.
There's no one-size-fits-all solution in railway engineering.
Every choice, from track gauge to axle load to suspension design, involves considering trade-offs and priorities.
It's like choosing the right tool for the job.
Sometimes you need a powerful freight train.
And sometimes you need a nimble mountain goat.
Love that analogy. And it speaks to the incredible ingenuity that goes into every aspect of railway design.
It really makes you appreciate the thought process behind something as seemingly mundane as train tracks.
Now, we've been talking a lot about traditional ballasted track.
The kind with the crushed stone base.
Right.
But is that the only way to build a railway?
That's a great question, and it brings us to a fascinating area of innovation in railway engineering.
While ballasted track has been the standard for centuries?
There's a newer approach gaining traction, slab track.
Slab track. That sounds interesting. Tell me more. So, slab track. It's like pouring a whole foundation just for the train tracks, right?
Yeah.
What are the advantages of that?
Exactly. Instead of using crushed stone, slab track sits on a solid concrete base. It's much more rigid than traditional ballasted track.
Okay, so it's strong and stable. I can see why that would be a big deal, especially for high-speed rail.
Absolutely. That rigidity is a game changer for high-speed lines. Even the slightest track movement can be a big deal at those speeds, so that stability is crucial.
It's like the difference between driving on a bumpy dirt road versus a smooth highway. More stability means a smoother, faster ride.
You've got it. But the benefits go beyond just speed and smoothness. Slab track also requires less maintenance.
Really? Why is that?
Well, think about it. There are fewer moving parts compared to ballasted track, and that solid concrete base is less prone to problems from weather like erosion or settling.
So no more shifting ballast or weeds growing through the tracks. That sounds like a dream for anyone who maintains these systems.
Exactly. Less maintenance means less downtime and lower costs over the long term. Of course, there's always a trade-off.
There's always a catch. What's the downside here?
The initial cost building slab track requires a much bigger upfront investment compared to traditional ballasted track.
So it's a classic case of pay now or pay later. Invest more at the start for those long-term savings.
Precisely. It's a complex cost-benefit analysis, and many factors are at play. Traffic volume, speed requirements, even long-term infrastructure plans.
It's amazing how even something like choosing between different track types involves so many considerations.
It's all connected. These decisions highlight how infrastructure projects are about finding the best solution, not just picking the newest technology.
It's a great reminder that even something as simple as a train track is the result of countless decisions, compromises, and innovations.
That's what makes this field so fascinating. And as we look toward the future with demands for faster, more efficient, and sustainable rail travel, increasing these engineering decisions become even more critical.
So what's next for railway technology? What other innovations are you most excited about?
Well, we focused on the physical tracks themselves, but there's a whole wave of digital innovation happening too. Advanced signaling systems, automatic train control, even using artificial intelligence to predict maintenance needs.
It sounds like the future of train travel will be smoother, faster, and even smarter.
And who knows, maybe our next deep dive will explore those very innovations.
I can't wait. But until then, we've journeyed from the clever weight distribution of ballast to the almost invisible dance of conical train wheels. We've uncovered the secrets of axle loads, track gauges, and that surprising link between frequency and passenger comfort.
And we've explored how engineering choices are never made in a vacuum. Factors like geography, history, and even politics all play a role.
So next time you're at a train station, take a moment to look at those tracks with new eyes. What seems simple at first glance is a testament to some truly ingenious engineering.
As we've learned today, there's much more to train tracks than meets the eye.
This has been an incredible deep dive. You've officially earned your Train Track Expert badge. Until next time, keep exploring, keep learning, and never stop asking why.